where meeting is being recorded. All righty. Good morning, everyone. This is Fred Rank from FHWA. I am a safety engineer with FHWA's Resource Center. This morning's webinar is the HSM applications to suburban urban multi-lane intersections. This is the third in a series of webinars that FHWA is conducting to deploy the Highway Safety Manual out to users. We know and understand that the HSM is, as being printed by AASHTO, is still not reaching and hasn't been shipped to all the users who have ordered it. The information that's provided in this webinar this morning is from the draft edition. The values as to coefficients and the equations will be the same in the final published version. What I'd like to do now is get started and give you some information on the Highway Safety Manual. The webinar this morning is one that's seen of great value by many transportation professionals, many practitioners. It meets and addresses so many needs and answers so many questions that if for projects involving suburban urban multi-lane intersections, that we FHWA moved it up in the beginning of the series. And secondly, this session on multi-lane urban suburban intersections will allow you, the practitioner in using the Highway Safety Manual, to build upon this knowledge in our following webinars. The first session of 3 for this morning's webinar is some introduction and background information. I'm Fred Rank, a safety engineer with the FHWA's Resource Center, working on the safety and design team. And FHWA has developed these webinars and is conducting them in conjunction with AASHTO as part of the deployment of the Highway Safety Manual itself. For our first session, we're going to review the safety performance of suburban urban intersections and also provide to you information on substantive safety and the substantive safety philosophy. That is an addition and how we transportation professionals have typically practiced our profession in the past. It's a significant change. It's a significant shift in a positive manner for our profession. Why intersection safety? Well, intersections are only a small part of our overall highway system. Intersections by themselves are not a very major portion of the overall highway system mileage, but intersections contribute 21% of total highway traffic fatalities each year. In 2008, 7,700 fatalities were related to intersections. Each year, more than 2.16 million intersection crashes occur. And this is the important part for you, the practitioner, to keep in mind. More than half, over 55% of all reported crashes occur at intersections or are intersection related. Intersections are an important part of our highway system, and they contribute a significant number of crashes overall. Overall, 2008, in terms of stop control or no control when signalized control intersections, together they constitute for total crashes about 55%. If you combine fatal and injury crashes, they constitute 57%. This is a significant problem, a significant portion of our overall safety situation that we have in the United States. Intersections play a big, big role in the overall traffic safety picture. In terms of intersection fatal crashes for 2008, 60% were in urban streets, 61% of fatals were on arterials, more than half in daylight, nearly half were right-angle collisions, 91% occurred in dry pavement conditions, 32% occurred at signalized intersections. And this is something that you need to be aware of as transportation professional, that signalized intersections are about 1 out of every 11 intersections in the United States. So fatals and crashes for signalized intersections, just based on their number out of all of the intersections, you'd expect to be down in the range of 9 or 10%. That is not the case. For fatal, injury, or PDO crashes, signalized intersections have somewhere between double and triple the number of crashes that on a basis of their numbers in the overall population of intersections. Some key things for you to keep in mind about intersections. Even today, our knowledge of how operations at intersections work and, more importantly, of safety performance of intersections remains somewhat imprecise. Your exercise of engineering judgment, it remains an essential part of the practice of transportation engineering. Just because you meet and comply with a nominal requirement in a standard for geometric design or operations of your state DOT or your area does not necessarily make it a safe intersection or a safe highway. Just all it means is that you satisfied the nominal value for your design standards. Some important features of highways are not determined by standards, such as spacing of interchanges and intersections, large radius right turn lanes, overhead signal per lane with a backplate known as a primary signal. These are not determined by standards. They're best practice associated with them, but each of these items are not typically specified in the Green Book or the MUTCD. They're more in some agencies standards, but not pervasively over a whole state. In the past, prior to about 1995, we typically thought of meeting the minimum requirements for the length of a transition into a horizontal curve, or the length of a tangent between two back-to-back curves, or for cross slope and super elevation. As long as we met those nominal requirements or exceeded them, the expectation would be that we would get a safe design. I think a better way to look at this, and one that you may want to keep in mind, is what in satisfying a nominal requirement, you satisfied the requirement in name, and hopefully you've gotten in name a certain level of safety performance. Now that we know more about how geometric features and operational issues with intersections directly relate to the crash frequency associated with those items, we can better understand how they contribute to substantive safety. Substantive safety is the actual crash frequency or the actual crash experience for a piece of highway, a roadway, or an intersection. And the substantive safety philosophy, as set forth by AASHTO in the forward to the Green Book in the third paragraph, states very simply that those locations, that although they may be nominally less than their standard amount, as long as they do not have an adverse safety performance, may remain in place as they were constructed. The substantive safety philosophy is knowing where crashes occur and how they affect the piece of roadway or the intersection that you're working on as a design or an improvement. It is incumbent upon all of us in the transportation field today to understand that our profession has been changed, that we are expected to know and practice the substantive safety philosophy in our work and incorporate it into the decisions in projects. That is, to know where the crashes are occurring and how they relate to specific aspects in your project, and then to address them in any improvements. To give you some better idea of how to characterize nominal safety and how it differs from substantive safety, let's go through some aspects of nominal safety. In the past, we typically based our engineering standards for design and operation on research and primarily on operational experience. The thought of a standard was to provide a consistent level of quality to the design or its operation. Typically, design standards are reflective of general cost effectiveness of the measure, such as the width of a shoulder, that we know that wider shoulders cost more to construct. We're typically moving the footprint out, the drainage further out from the edge of the roadway, and hence any increase in shoulder width gets more and more expensive. So how much do we gain for the additional width of a shoulder? And hence most states have policies that follow the AASHTO policy of a 6-foot minimum shoulder width related to cost effectiveness. That's the aspect known as nominal safety. I would like you to consider nominal safety as the first step in the checking of the quality of a set of plans for improvement. Do you comply with the minimum requirements of your state design standards of the MUTCD for operational requirements? Additionally, and I'd like to give you an example that relates to intersection traffic control. First step, there's a requirement for 2 signal indications for a major movement, and this has been in the MUTCD in Part 4 signals since after World War II. And you may accomplish and meet that standard by doing a near right and a far left post mount, which is depicted in this photograph from Jefferson City, Missouri. Second step is to go beyond the nominal requirements and do signal head per lane with backplates, as this example shows from Montana. We know that going to a primary head per lane with a backplate reduces crashes by 30 to 35%, and we get a 15 to 45% reduction in severe right angle crashes. Substantive safety is knowing how your crashes are occurring, where they're occurring in their crash patterns, and then applying measures that directly address that known safety experience. The MUTCD was changed for 2009 edition as guidance that for higher speed approach roadways, 45 and above, the MUTCD now gives us guidance. You should use signal head per lane with backplates to increase visibility, enhance that visibility of that signal indication to the user. We know it's safer, and it goes beyond the nominal requirement of 2 signal indications for the major movement at a signalized intersection. In the Highway Safety Manual, we gain a significant change, and that's most important to the overall practice of transportation engineering. For a number of years now, we have been able to assess the environmental impact of various alternatives in a project. We can do an operational analysis on operational adequacy in terms of level of service of an existing facility, or use HCM software of a proposed alternative. We can certainly do the costing and an economic analysis of various design alternatives. With the Highway Safety Manual and its modeling, and how it can account for site-specific conditions that differ from the base assumed conditions of the model, we can actually quantitatively assess the safety impact. And by doing so, we can get safety in a quantified, reasonable, pragmatic form into the decisions being made on a project. The new Highway Safety Manual of 2010, its methodology is a lot like that of assessing and assuring the adequacy of capacity, which we can do with the Highway Capacity Manual. The Highway Safety Manual will allow transportation professionals to understand and quantify highway safety, crash frequency, performance in an informed and balanced decision-making manner. The HSM is a set of tools. It's for mathematical modeling and for mathematical analysis of the relationships to safety, geometric features to crash frequency performance based upon exposure and roadway conditions. It's a set of analysis tools only, just like the Highway Capacity Manual. It does not have standards nor best practice. The MUTCD has standards and best practice. The policy on geometric design has best practice, and only 4-ish items in the entire Green Book are actually standards. The HSM does not supersede other publications that do have guidance and standards. So the Highway Safety Manual is not like the MUTCD. It's not like the Green Book. It is for analysis tools only in the same and like manner as the Highway Capacity Manual. So the HSM, a set of tools, and those tools will allow us to predict crash frequency based upon exposure, and that is in terms of average daily traffic or traffic volume and specific conditions for certain, such as a two-lane road, or as a multi-lane rural road, or as an urban suburban multi-lane roadway. Is the intersection two-lane rural? Is it multi-lane rural? Or is it an urban suburban intersection? Is it stop controlled, or is it signal controlled? We have sets of tools, models for the prediction of crashes for each of those types of intersections. And we can analyze that crash frequency that we predicted and adjust for it and with specific crash modification factors for the actual conditions of the intersection we're studying. So we can facilitate explicit consideration of safety throughout a project development process. The HSM provides probably the best synthesis of validated highway safety research. There's certainly a lot of research out there linking geometric items and operational items to safety performance. The HSM took a large, long, and hard view of that great body of information that's available out there and said, which of these are rigorous and have the highest statistical rigor that we can provide to transportation professionals for their use, that they will get these observed crash frequencies if they put this technique, this remedy, incorporate this feature into their projects. The HSM provides analytical tools to predict the decisions on road safety. So the new HSM contains the best of science and research. How can crash prediction be used? Well, at various levels. At the program level, in terms of prioritizing individual locations or intersections within a list of projects being considered. At the project level, to assess the needs of the project as you start the scoping, as you start considering the design features. And very importantly, to be able to communicate safety and safety performance within those needs to the public, be able to prioritize the work within a project to keep it within its budget, and most importantly, give you the documentation for the exceptions, for the decisions that you're making in a project, and if you have a design exception, to show how you plan to mitigate in an adequate manner any design exceptions change in safety performance. If you use it properly, you can certainly use the Highway Safety Manual to assist you in quantifying the relative safety of facility and demonstrating that you, in working for a public agency, are addressing safety needs appropriately. You should keep in mind that FHWA, in a program memorandum, has made it a policy that safety must be fully considered in every aspect of a project, from the planning through construction, maintenance, and operations. And that's been in place for more than 5 years now. So if quantifying safety using the Highway Safety Manual, well, can allow us to get safety into the decision-making process in a quantitative manner, this is a good thing, and it will make for good design and good design decision-making. The role of road design in crash prevention. We know that the human being in the driving task routinely errs. It's the nature of the human brain in the driving task. The human brain is a parallel processor, starting from the same input sensory information, branching to a decision in driving. Well, in a parallel processor, that branching can differ. It's not reliably the same each and every time, starting with the same inputs. And this parallel processing and inherent errors result in errors in driving. And what the part that we as engineers can influence is not so much will the driver err. We need to anticipate and expect drivers to err. But what we affect by our engineering is will that human error result in a crash, and will that crash be severe? How you design a particular section of highway or an intersection and how you operate it affects both the number and the severity of crashes. And that's the portion that we as engineers affect. So what can the Highway Safety Manual do for you? Can it predict safety performance of geometric design features? Length of tangents, tapers, median widths, configuration of left turn lanes, right turn lanes? And the answer is yes. Can we quantitatively calculate these safety effects of changes in crash frequency? And the answer is yes. Predict safety performance of intersections as they exist today or as we plan to improve them? Yes. And definitely yes to all of these items really get safety into a quantitative process by using the Highway Safety Manual. Better decisions for safety as a result? The answer certainly is yes. So in this first session, we've introduced you to the safety performance of suburban urban intersections so you can better understand them and how they affect overall traffic safety. And we've identified to you and defined how substantive safety goes beyond nominal safety and how substantive safety and the substantive safety philosophy are now integral to the practice of transportation engineering. Second session today will be the prediction of crash frequency for suburban multi-lane intersections. We're going to describe the models to predict crash frequency for multi-lane suburban intersections in this module. AASHTO has not yet provided the final exhibit numbers to FHWA. So the material that I'm going to be showing you in the slides is from the draft prior to publication of the Highway Safety Manual. So what we expect is that the exhibit numbers may change, may not exactly be the same, that an exhibit 12-46 may not end up being 12-46 in the final printed HSM. It may change to 12-32. Additionally, crash modification factors are identified in this draft and in the exhibits as AMF, or accident modification factor. AASHTO made a conscious decision to convert AMF to CMF, or crash modification factor, in their final published version of the HSM. This is a good move. It's better defined. It's a more definitive term. It's AMF had been previously used by many of the researchers over the years. CMF, or crash modification factor, probably is a better way for the terminology of what's being used, a factor that you can adjust your predicted crash frequency for the actual site conditions at an intersection. The presence or not of a left turn lane or a right turn lane, the presence of no turn on red, the type of phasing of a traffic signal, whether it's permissive only, protected permissive, or protected only. Are there red light cameras present? Each of these lighting, these are crash modification factors that have a known safety linkage and are quantifiable in terms of affecting crash frequency. First, definition of intersections and segments. The HSM is a functionally organized document, and the answer to many questions about the Highway Safety Manual can be put into that format of the question. Think functionally when you go to answer a question you may have in terms of applying the Highway Safety Manual. We measure the length of a segment from the center point of an intersection to the center point of an intersection, typically, or to a point where the cross-section width changes or ADT changes in a significant amount or other design features. That said, crashes are assigned to intersections as within the intersection itself and within its functional area. Intersections may be signalized, stop controlled, or they may be roundabouts. So we have the functional areas as well as the physical area within an intersection. And the functional areas are the approaches to the intersection, its queue length, as well as its downstream portion. So I would like you to think of the functional area of each approach as consisting of three basic elements: the decision distance, the maneuver distance, and the queue storage distance. As the very first part of that decision distance is the recognition, beginning the perception reaction process of there's an intersection and it's up ahead. And it's really important that the driver know that this is a change, that they're going to have to look for cross traffic and stop traffic, then change their driving speed and path in approaching an intersection. So we have the decision distance starting with the perception of intersection ahead. Then we have the maneuver distance of beginning to any needed deceleration to complete it at the back of the queue, and then we have the queue storage or storage length as we approach the intersection. That functional area is known as the impact length, and crashes within the impact length or functional area are related, directly linked, and tied and associated with the intersection itself and any driveways within that area. And those crashes are not assigned to the segment, but more they are assigned to the intersection itself. So crashes in organizing information for segments and intersections, we assign crashes that are within the functional area, that impact length on the approaches to an intersection, to the intersection itself. Again, we have perception reaction distance, the maneuver distance, and the queue storage distance as our total functional intersection related area on each of the approaches. There are specific safety performance function models for the prediction of crash frequency based on 4 types of collisions. First, we have multiple vehicle crashes between vehicle to vehicle. Then we have single vehicle collisions of a vehicle by itself, not striking or being involved with another vehicle, but rather be striking a fixed object or leaving the roadway, such as a vehicle that hits a traffic signal pole. Additionally, we have vehicle pedestrian collisions and vehicle bicycle collisions. The process of calculating and combining the various types of collisions for suburban urban multi-lane intersections is the second most complicated thing we do in the Highway Safety Manual. Probably the most difficult is over in multi-lane urban suburban, where we have to deal with driveways by type. And I'd probably think of this as the prediction of crash frequency for suburban urban intersections is probably the second most complicated. So let's get started. Now that I've told you and sort of warned you in a way, this is somewhat complicated, but it's still far easier than previous methods and methodology in how to determine a crash frequency, predict a crash frequency for intersections that we knew in the 70s and the 80s. So first, our safety performance function for an intersection will be the combination of the predicted crash frequency for multiple vehicle crashes plus the single vehicle crashes. We're not going to yet address ped and bike crashes. That comes later in the calculation process. So we'll first predict the number of crashes, the crash frequency for multiple vehicle crashes, and then for single vehicle crashes and combine them. We have 4 types of right-of-way control for each of the multiple vehicle and single vehicle crashes. We have 3-legged intersection stop control, and this has only 1 stop sign, and that's on the minor road approach or the stem of the T. 3-leg signalized intersections, which is the 3SG model. The 4-leg intersection with stop control on the minor road approaches. So a 4-approach intersection stop control for Highway Safety Manual modeling has only 2 stop signs, and they face the minor road approaches. 4-leg signalized intersection is the 4th type of model. So our crash frequency prediction for multiple vehicle crashes is in the format of EXP, which is natural E, LN is natural log. and we have A, B, and C coefficients. And these A, B, and C coefficient values will vary based on whether it is vary by the type of intersection control, whether it's 3 or 4 approaches, whether it's stop or signal control. So our ADT of our major road is the larger of the ADTs of the 2 intersecting roadways, and the lower value ADT is the minor. Do not switch them, you'll get unreliable results. The coefficients for A, B, and C are shown in Exhibit 12-19 from the Draft Highway Safety Manual. These coefficients, we expect no changes in any of these values. So the material for this morning's webinar, you may download in the file share pod if you did not also do so before the webinar started this morning. You may do so afterwards, and we have it up in the file share pod from the presentations. You can download these and print these as your working copy of the Highway Safety Manual until you receive the printed copy from AASHTO. So our A, B, and C coefficients have differing values based on whether it's the 3ST model, the 3SG, the 4ST, or the 4SG model. And this is for multiple vehicle crashes. The coefficients for single vehicle collisions will be different from these shown in Exhibit 12-19. In fact, we have coefficients for fatal and injury crashes only and for property damage only crashes by the type of intersection right control, 3 or 4 approach, stop, or signal controlled. Single vehicle non-driveway crashes. Again, the same format of the equations, same with A, B, and C coefficients, but the values for A, B, and C will differ. And I show you these in Exhibit 12-25 by the 3ST, 3SG, 4ST, or 4 approach signal controlled intersection. Again, for single vehicle crashes, we can look at total crashes or just fatal and injury crashes and property damage only crashes. By and large, the Highway Safety Manual is working in predicting crash frequency of total crashes. For some aspects, such as intersections, we also have available the coefficients and the models for dealing with fatal and injury crashes only, or for dealing with property damage only crashes. And we have these for suburban intersections, which we're showing here. As an example, 4 approach stop controlled intersection, 25,000 ADT on the major road and 5,000 on the minor. We would first calculate our crash frequency for multiple vehicle crashes, then for single vehicle crashes, and then combine them. So first, for multiple vehicle crashes, our A coefficient is minus 8.9, our B coefficient is 0.82, and our C coefficient is 0.25. We would plug in our ADT for our major roads, 25,000, and 5,000 for ADT of the minor road, and calculate the value. Be about 4.63 crashes per year. Now, one of the things that's going to leap at you very quickly as you first start to use the Highway Safety Manual, as you look at the calculated values, your first reaction naturally may be, gosh, these values look small. I'm used to dealing with intersections that have 25, 40 crashes a year at larger ADTs, and these predicted values are rather small. That's normal, that's expected, and I'll explain a little further in detail as we go along. Don't be surprised if some of the calculated values appear low as you first start using the Highway Safety Manual. For single vehicle crashes, our A, B, and C coefficients from the table, from the exhibits, are different than for multiple vehicle crashes. A is minus 5.33, B is 0.33, C is 0.12. And single vehicle crashes within an intersection typically tend to be about 1/10 of the value of multiple vehicle crashes. We could not combine both into the same predictive equation and get reliable results. By separating them, we could, and hence that's how they're organized recognized and set forth into the Highway Safety Manual. So now addressing we're going to combine the multiple vehicle crashes and the single vehicle crashes together. In this case, 4.63, and then add the single vehicle crashes to get the net result of 5 crashes a year. For the most part, the intersections that you deal with in your practice of transportation engineering tend to be those locations that have safety and operational problems and shortfalls. Your more typical experience will be of dealing with intersections that have 15, 20, 30, 40 crashes a year. So when you first start using the Highway Safety Manual, you need to clearly understand that the predicted value from using the Highway Safety Manual represents the middle of the data set of these huge data sets that TRB, NCHRP, and FHWA put together, from which the Highway Safety Manual equations were developed. And these are data sets from multiple states, and they're very representative across the entire United States because of which states they were. Minnesota, North Carolina, Texas, California, Illinois, all contributed to these databases. And we would expect with any regression line equation that it goes through the middle of the entire data set. Your experience probably has always been in dealing with the intersections up at the higher end that are well above the middle. Yet this calculated values in the HSM represent the middle, or the expected average crash performance for an intersection at that ADT and at that type of traffic control. What happens if we signalize it? Let me go back one here. Okay, I want you to keep in mind that stop controlled, we had about 5.01 crashes predicted per year. Now for the same ADT, let's signalize it. 25,000 meets 5,000. We have different A, B, and C coefficients from the signalized intersection exhibit. We calculate the value for our multiple vehicle crashes and get 6.08. Using the equation for single vehicle crashes for a signalized intersection of those same ADT values, the single vehicle crashes are about 0.36. We combine the two for a signalized intersection and get a sum of about 6.44. Now notice that the number of predicted total crashes is higher for a signalized intersection than for the same exposure, same conditions as a two-way stop. This is actually the experience across the entire United States, that signalized intersections for the same exposure have more crashes than a two-way stop. And inherently in this is the basis and the reason for this, that you're now controlling the through traffic on the main road. And under signal control on a recurring cycle length basis, you're slowing and stopping on yellow and red the mainline traffic. Drivers err on seeing, perceiving yellow and red, reacting in time and stopping in time. And the higher number of crashes is due to the human error on having to slow and stop on main line. Next step is to apply crash modification factors to our combined predicted crash frequency for some multiple vehicle and single vehicle crashes to account for where we have conditions either existing or proposed in our design improvement that will differ from the base conditions. And then after we've applied the CMFs, we would then add in the PED and bicycle crash predictions into our total crash prediction for the entire intersection. C sub I is the calibration value for the equation. At this point in time, be very careful about using the calibration factor for a particular area or for your state. Some states have done adequate and doing really good work in advancing how their values in an individual state may differ from the base values of the Highway Safety Manual. Many states are just now getting underway with using Safety Analyst as one of the software systems that analyze their crashes statewide to know what an appropriate calibration factor would be. Until at such point in time as your agency has done, carried out, and is satisfied with the results of their multiple years of analysis of crash experience, the Highway Safety Manual value of 1.00 is a good starting point. Until at such point as you have more definite information for your geographical area. And the Highway Safety Manual at this point in time does not have a listing for calibration factors for states or geographical areas. Rather, it has just the value of 1.000 for any location within the United States. So in this second session, we've described the models for the prediction of crash frequency for multi-lane suburban urban intersections. In our third session of this morning's webinar, we're going to describe to you and the crash modification factors for multi-lane suburban intersections. These differ. In some ways, they may be similar, but they differ from those CMFs for rural two-lane highway intersections and for rural multi-lane intersections. We're going to apply these crash modifications to predicted crash frequency and provide to you examples. In our previous session, we described to you the model to predict crash frequency for intersections, where we combine single vehicle and multiple vehicle crashes into our SPF for intersections. And our crash modification factors for intersections are 6 in number, and they are for the following geometric or operational conditions: for left turn lanes, for right turn lanes, for left turn signal phasing, for right turn on red, lighting, and red light camera photo enforcement. In the first edition of the Highway Safety Manual, these 6 are the only CMFs for multi-lane urban intersections. First is for left turn lanes. Of all of the geometric features, left turn lanes have probably the biggest effect of any of the geometric measures. They have various CMF values ranging from 0.67 all the way up to 0.93 in terms of their safety effect. A CMF AMF of 0.67 is a 33% crash reduction. A 0.93 would be a 7% crash reduction in looking at the column for one-lane approaches to minor road stop control traffic signal or for 3 or 4 leg controlled intersections. The CMF applies only to the uncontrolled major road approaches for stop controlled intersections. So these values in 12-41 apply just for the uncontrolled major road approach for stop controlled only. For signal control, those AMFs, CMFs apply to all approaches. Left turn lane on one approach for a 3-leg intersection, and this exhibit is from Chapter 14 of Part D, beyond Part C of the Highway Safety Manual. It is not in the crash prediction chapter number 12, but is auxiliary further information provided in Part D of the Highway Safety Manual. Additionally, from Chapter 14 is effects of providing a left turn lane on one approach of a 4-leg intersection, on 2 approaches to a 4-leg intersection, and these materials will show up just that way if you download today's webinar presentation, so you will have the information. The second CMF is for left turn signal phasing. The base condition is permissive left turns, and that CMF value is 1.00. Protected permissive or permissive protected operations 0.99, protected only is 0.94. Left turn crashes do not constitute the majority of the crashes at a signalized intersection. Hence, the Highway Safety Manual in predicting and in working with total crashes, you don't see that big of an effect of a change in left turn phasing on total crash performance. If several approaches have left turn phasing, you multiply the AMF CMF for each of those approaches. So if we have 2 approaches protected, and that would be protected left turn only, we would multiply the first of 0.94 by the second CMF of 0.94 and get 0.88 for the net results CMF for signal phasing. The third CMF is for the presence of right turn lanes. The values are about half of that for left turn lanes. We can also account for whether we have right turn on red or do not have right turn on red. For example, if we had 2 approaches, we would then multiply the 0.98 by the raised to the exponent of 2 for those 2 approaches and get the net result of 0.96. For no approaches, the ACMF would be 1.00. Lighting is a known linked safety measure. It can reduce crashes primarily of nighttime crashes, and nighttime crashes tend to be for less traffic than during the day. So lighting, a known safety measure directly affecting nighttime crashes, doesn't have that big an effect on total crashes, and the HSM was working in total crashes. For example, a 4-approach signalized intersection with no lighting, we start to use the calculation, but please realize, if it's unlit, that's the base condition, so our CMF is 1.00. Actually, with lighting and applying the appropriate P sub NR of 0.235 from the exhibit, we get the effect of 0.9107 for lighting effect on total crashes. Red light running enforcement for cameras. This is CMF is from Chapter 14 for intersections in Part D. It is not in Chapter 12 for intersections by themselves. It's an additional piece of information. So applying all of them together as an example, a 4-leg signalized intersection, 25,000 ADT meets 5,000, left and turn and right turn lanes on the major approaches. It's lighted, and we have protected left turn phasing on the major road. We know our predicted value is 6.44 from the previous session in which we calculated the crash frequency for 25,000 meets 5,000 signalized. So we will have our CMFs 1, 2, 3, 4, and 5 and 6. And they were for left turn lanes, this is CMF 1. CMF 2 is for left turn phasing. With CMF 3 is for right turn lanes. 4 was for no turn on red, which there were none of these approaches were posted, so it's 1.00. Lighting, 0.911, and red light cameras is CMF 6, and there were none present for this example. So in doing our calculation, we take each of the CMFs, 1 through 6, and we multiply them together, and then by the crash frequency. So 3.85 crashes per year is what we would expect after multiplying the appropriate CMS to our crash frequency prediction. Now at this point, you know several good important pieces of information. And here is the real strength of the Highway Safety Manual to you, the practitioner. Let's say this intersection of signalized, 25,000 meets 5,000, was experiencing 12 to 15 crashes a year for these geometrics and operational conditions. And your predicted value is 3.85 crashes per year with the CMF supplied. At this point, you know that this predicted value is your starting point. This predicted value with the CMF supplied is what nationally we would expect for that ATT exposure and those site conditions for that location. The difference between 3.85 and 12 to 15 crashes a year of actual crash experience is the difference. And that difference in crashes is the amount that you will need to address and remediate and improve in any proposed project in the intersection to get the safety performance, that is the crash frequency performance, back to at least the normal we would see for an intersection of that traffic level and that configuration. So with the Highway Safety Manual, the crash prediction can give us a starting point, and then the difference between that predicted crash frequency to the actual, it gives us a measure of how much safety difference we need to address in our project. We would then add to that predicted crash frequency with the CMS applied. We would then add the predicted number of crashes for pedestrians and bikes. And both of those procedures, let me go back one slide, both of those procedures are fairly lengthy, and we're actually going to cover them in a major webinar as part of this series. That webinar will be conducted for pedestrians on July the 12th. And so you can expect this part to be specifically addressed in detail in the following webinar as scheduled. So in this third session, we've described to you the crash modification factors for multi-lane suburban intersections, the crash modification factors available to account for your conditions and where they differ from the base model. At this point in time, I'd like to entertain questions for discussion. And what I'm going to do is bring up the questions that were in the chat pod. So we may, I can provide to you the information that should help you. Just a moment, let me bring up the questions from the chat pod. Yes, the first question was from the North Dakota DOT group. If the ADT values are quite different upstream and downstream, should we simply use the highest ADT? And the answer is yes, and that is the preferred method, rather than averaging the ADTs of each of the approaches to the intersection. Use the higher value for ADT major, and on the minor road, the higher of the minor road intersections. Question from Dave Gee, Dave Schaefer. I noticed in one of the previous slides, formula values are given in ADT, and the table slide is given in AADT. Either of those are used, the terminology, both are used in the Highway Safety Manual, and what they're really seeking is what's the average daily volume. Yes, there is a minor difference in the value between ADT and AADT. The Highway Safety Manual does not distinguish between the two or make a big deal of them. Anthony Bruzak, will calibration factors be different for every HSM module for a given area? That's possible, and it would be the results from safety analysts for your state if they conduct it for specific geographical areas. But that's something that's in the future, and it's going to be very dependent about how fast your state progresses towards developing its own calibration factors for the state, and will they have different ones for different areas. Gil from New York State DOT, how does this apply to a single point intersection and roundabouts? Single points are spelled out specifically, and there is no information in the HSM on single point intersections. There is for roundabouts, and primarily the information is over in Chapter 14, and there's an extensive amount of information in the form of CMFs for single and multiple lane roundabouts. And you would apply that roundabout to either a stop-controlled or a signalized intersection crash prediction. There is, at this point, in time, in the first edition of the HSM, no separate models for roundabouts. So you first of all would need to do a prediction as a two-way stop or a signal for the intersection in those volumes, and then apply the appropriate CMF to account for the roundabout design. From Stephen Rathke, Texas DOT has funded research that calibrates the HSM to Texas, and that's available on a statewide basis in Texas. Yes, and TTI did the work. Bonison, Paul Carlson, and others worked on that, and they've calibrated it for the state of Texas for their use in Texas, and is the first of the individual calibrations that I'm aware of the base models. So almost all the models are the same. They have a few additional factors that they have developed and used, such as access density and driveways within 250 feet of an intersection that we do not have in the national manual. A question from Jason Osmond: how about the severity of collisions at signalized intersections? Will it decrease significantly by signal according to this model? In fact, it's yes, you can account for that, and the way to do it is to do your crash prediction frequency as stop controlled using the coefficients for fatal and injury crashes, and then as a signal for fatal and injury crashes. Would it be expected to decrease significantly? You'll have to do the math. There is an excellent NCHRP report on this very issue called NCHRP 483 on traffic signal warrants and traffic signal crash warrant. From the Chicago Department of Transportation, is there a formula or an adjustment factor for intersections with more than 4 approaches? And the answer is no. There were, in the databases of the states, there were so few intersections that had more than 4 approaches, they could not develop a reliably, statistically valid model for 5, 6, or 7 approach intersections, and hence they are not included in into the HSM. Question from Farah: how many approaches do we have on a 4-leg approach, 2 or 4? We have 4 approaches on a 4-approach intersection. If it's a stop control, only 2 of those approaches will be stop controlled and the other 2 will be free moving. From Palmer: it sounds like an intersection with an all nighttime crashes would yield a high rate of return for lighting. And the answer is yes. And that's one of the outcomes of the Highway Safety Manual, is that you're able to statistically model and predict a change in performance of crashes based on the application of a countermeasure, such as lighting. From North Dakota: is there a way to account for arrival types, such as in one direction is favored and the other direction has poor signal progression resulting in rear-end crashes? And the answer is no. The HSM is not that detailed at this point in time to be able to do that kind of analysis. That's more of an operational analysis. With traffic signal progression is an operational issue. This first edition of the HSM takes us a long way. It provides a good, comprehensive methodology. It includes and specifically identifies many key important geometric and a few operational features. It is by no means a complete document addressing all aspects at this point in time. Maybe by the 3rd, 4th, or 5th, or 6th edition, it might. But the first edition gets us started. It yet does not have that kind of level of detail. From the City of Bloomington: is there any data regarding whether or not more or less green time for a particular movement decreases or increases crashes? And the answer is no, not in the HSM at this point in time. Can we make an argument that green time in signals may need to be timed for safety in some cases and not necessarily for capacity only? Yes, but that information is not in the HSM at this point in time. It's available, and there are several good NCHRP and TRB papers available that answer that question. The question from Shala: how about vehicle transit collisions? The answer is no, they're not specifically identified in the HSM. We are only able to identify total crashes single vehicle crashes, multiple vehicle crashes, bike and ped. And that's as far as the detail level goes at this point in time. From Pima County DOT, if the CMF for left turn phasing only for protected only left, is this for a red, yellow, green, and left turn arrowhead, or does it include the use of protected permissive left turn 5-section head? No. The answer to your question is it is for left turn phasing only as a 3-section head, or if it's a advanced left, that's left running only, it could be done as 4-section head, which is your first alternative. The protected only means that no other phases or timing. It is just timing for as a protected movement to left only. The key aspect is that then you're not clearing the permissive left turns on yellow ball, and that's the difference in the safety performance. Gil from New York State asked, is there more extensive training available via the classroom? And the answer is yes. Currently today, the same material from the draft HSM is the basis of the National Highway Institute's 380076A and B courses. They're currently labeled as safety effects, but the material is the draft highway safety manual, which we're conveying to you in this webinar today. We will rename those, and they may get new session numbers in the NHI catalog as a result of being retitled when the AASHTO printed HSM is out in circulation. We, FHWA, will make the choices and make the changes and convert it over. LCG Traffic asks, will the HSM include flashing yellow arrow analysis? The answer is no. The information just isn't as far along as we'd need to be to go into the HSM yet. Dr. David Noyes, who did the reported crash safety analysis on flashing yellow arrow in Web Document 123, said that that is the case. We need more years of data and more locations in order to develop what we would call a statistically reliable CMF. From North Carolina DOT, how did the manual define and determine urban? It's the AASHTO definition. If you're outside of an area of 5,000 or more population, you're rural. If you're inside an MPO or an area of 5,000 or more population, you're urban. But I'd like to take you back and revisit one of the very first things we covered in today's webinar. Think functionally and don't think long. Functionally, if it looks rural, it acts rural, it's performing rural, use rural to analyze it. If it's urban-suburban and it looks that way, then use the urban-suburban methodology and the coefficients and the crash prediction models. From Joe, why not use actual crash counts as the baseline? And in fact, you can. And that methodology, that way of looking at crashes, is covered in Chapter 4 and in Appendix C of the Highway Safety Manual. And it's the empirical Bayes method to predict the estimated number of crashes, which is the next step beyond what the mathematical results that we showed in this webinar. From Mark Gorger, if the HSM analysis shows that the existing conditions are better than the new policy, then do you forego the policy? I'll answer that in two parts. First of all, the HSM is an analysis tool. The set of models and how to adjust them for crash prediction. Your policy is your policy. You could certainly use the analysis of HSM in a review of your policy to modify it. But by no means does it replace your current policy. Merely it's a set of tools to analyze safety and for you to have it as the practitioner to have a deeper understanding of how geometric features and certain operational effectors affect safety performance. You may choose to do that, but your policy is your policy. You're just using the analysis tool of the HSM to review and modify. Question from Patrick Landry. what are the adjustments for skewed intersections? It turns out that for urban-suburban intersections, there are no effects of skew. Skew comes into play in rural two-lane intersections and in stop-controlled rural multi-lane. There is no effect for skew in the urban-suburban intersections that could be linked to safety performance. From Jason Osmond, what is the benefit of a signal safety improvement if no is the resultant benefit is a increased factor of collisions? Some things that we do actually increase crashes, and we do them for certain deliberate choices, such as installing median cable barrier in a freeway median or expressway. We know that the cable median barrier will catch and safely stop a vehicle that enters the median, and we prevent the extreme severe collision of a crossover on a high-speed facility. But guess what? The proximity of the cable median barrier to the inside edge of the travel lane actually increases total crashes, but we get the effect of fewer severe crashes. And that's one of the aspects of the Highway Safety Manual that comes out loud and clear. If you signalize an intersection that's a two-way stop control, you will typically increase the total number of crashes. But you may, and you hope intentionally, you'll be decreasing the number of fatal and injury crashes. From the Chicago Department of Transportation, will always stop analysis be included in future editions? And the answer is it's a CMF and covered in Chapter 14 to take a two-way stop prediction and convert it over to a prediction for always stop control. There is not a separate model for always stops, but there is you can use the two-way stop crash frequency predicted value and apply the CMF for always stop. From Louisiana, can you use the 3ST for one-way minor approaches? And the answer is not so well. You don't have both directions of movement, and hence it does not fit well. I would be mighty careful about that application. That's not to say that you can't do it. It's just going to take some deliberate care, and you're going to have to make some assumptions and changes as to the meaning of the results. From Patrick Landry, I did not catch the answer to what are the adjustments for skewed intersections. Let me say again, for multi-lane urban-suburban intersections, there's not a known adjustment nor a CMF for skew. From Sony, I am interested in software to predict collisions at rural intersections. That subject is actually going to be covered in a webinar presentation on the HSM on Tuesday the 29th. I would urge you to tune in, and we will cover that in the webinar, as well as provide in the file share pod a spreadsheet for the calculation of predicted crash frequency for rural intersections. And with that, I believe we've covered all of the questions that came in the chat pod. And with no more questions today, I believe we're ready to wrap up today's webinar. I believe that we've covered all the questions, and I hope that you've enjoyed today's session, and we look forward to having you at future webinars, and the next one will be on Tuesday the 29th. And the